Hi everybody. So here we go. This is our note on inverse functions. We did inverse functions in functions, grade 11. So this again should be mostly a review for you. This is a website called purplemath.com, and it talks about what the inverse is. So if my explanation leaves you still curious, you can go ahead to look on Purple Math and learn some more about an inverse. Really, the most important thing here is that the x's and y's have been reversed, like they say. So when you're getting to graphing, this has a really good way of getting you to graph your inverse. So if you remember, the inverse is just when you interchange the independents. So your x's become y's and your y's become x's. So they reflect across this y equals x line. So if you have a curve like this nice blue one, we don't even need the equation for it. You can come up with what its inverse would look like by just drawing this y equals x line. Okay, so that's directly, cuts the axis in half there. And then you can draw the reflections by saying, well, it would just be however much distance it is from this line, it would be that distance again in the other direction. Okay, so if this point, for instance, is 1, 2, 3, if that's about 3, 1, then on the inverse would be about 1, 3. Okay, because you switch x and y. And so then you can just draw the points that way and come up with your inverse curve, this purple one. Okay, and then there's lots more pages on purplemath.com. You can check out a lot more about the inverse there. So just another resource for you. So let's go to my note here on inverse relations. So our learning goals are to define what an inverse function is using the appropriate notation. If we're given a function, graph and describe its inverse. Restrict a function so that its inverse will also be a function, and then determine the equation of the inverse relation or the function if you're given the equation. Okay, so we'll be able to do those 4 things by the end of this note. Like I was saying, the inverse of a function, f at x, is denoted by f to the minus 1x. Okay, that's just the notation we use for the inverse. It is found by exchanging the independence of the variables in the equation, or table of values, or graph, etc. So I often talk about, the inverse in real life is like head down to shoulders, down to knees, down to toes. The inverse relationship of that would be toes up to knees, up to shoulders, up to head. So you're doing the opposite thing in the opposite order. Okay, you're changing where the dependence is. So if we have a graph, okay, any generic graph here. So let's say f at x starts here and goes up something like this. So let's say that this is f at x. Okay, so let's say this is the point 0, minus 3. Let's say it crosses here at 2, 0. Okay, so the inverse is found by reflecting over y equals x. Okay, so it should be exactly in between, like cutting these axes in half is what that should look like. Okay, so this is the line y equals x. And you're reflecting over here. Again, the x's and the y's just interchange. So instead of 0, negative 3, it's going to be negative 3, 0. Instead of 2, 0, it's going to be 0, 2. So see, there we go. We have the equal distance there. Okay, and then this section here, well, that means if you look across that, see it's bulging out a bit here. So this is a bit further out. So you'll have a point a bit further out there. So it's going to look something like this. Now, where do you think it's going to cross? Well, it's going to cross here because that's the line y equals x. And so if y equals x here, when you interchange x and y, you'll still just get x equals y, because this is the point where the x value and y value are the exact same thing. So that point will also be on the inverse because the x and the y value are the exact same thing. So it's going to cross there. Okay, now this is going up in this direction. So imagine there being a mirror here. It's going to kind of go in this direction, right? Okay, so again, if you're thinking about this in terms of reflections, it's going to be the equal distance from here to here as it is from here to here. From here to here as here to here, if you did it exactly appropriately. So from here to here is the same as here to here. That's how you get these points. Okay, so that's the graph of the inverse. Oops. The notation with an f there can only be used if the inverse is a function. Now, in our example up here, our inverse was a function. See, the red curve is a function. So actually, I should have labeled that way. Okay, but I can only use that notation if it is in fact a function, which it isn't always. So not all inverse relations are functions. And to ensure that it is, you may need to restrict the domain on which you're inverting the function, okay? So that when you do invert, you still get a function, okay? I left this for me to write in because this is so important. So if the point AB is on a function, then BA is on the inverse, okay? So because the dependent is just switching, you're just literally flipping the numbers to get your function. So if your function has a set of values like 1, 2, 2, 5, 3, 8, then your inverse function would have 2, 1, 5, 2, and 8, 3. So notice here that your x's become your y's and your y's become your x's. So that makes sense that the domain becomes the range and the range becomes the domain. Okay, so to solve algebraically for the inverse equation, we need to interchange x and y and then just solve for y. Unless, and this is a big unless, the variables have meaning. Okay, if you see an equation just like y equals 2x plus 5, those variables don't really have any meaning, okay? X in this case just means, hey, I'm the independent variable. And y just means, hey, I'm the dependent variable. So to change the dependence, we just would flip x and y, because now we're putting the independence over here and the dependence here, and then we would just solve for y. But in cases like, let's say, a equals pi r squared, a doesn't mean, hey, I'm the dependent variable. A means area. It's saying, hey, I want the radius to be, I want the area, sorry, to be dependent on the radius. But what if I want the radius to be dependent on the area? Well, then I just rearrange for r. I don't switch them. I can't change them because they have actual meaning. They don't just mean generic variables. Okay, so in this case, I would just switch, sorry, just rearrange. So here, area depends on radius. So we would use this equation if we knew radius and we wanted to find area. So here's our independent, here's our dependent. This is just a square root function, so it would look something like this. But the inverse, we want to switch it around. So we would have a over pi equals r squared. And then we would have the square root of a over pi equals r. Now notice I don't do plus or minus because radius cannot be I made a mistake there, didn't I? See? You guys are like, hey, Mrs. Beans, now we have to erase stuff. Sorry about that. How do I erase? Eraser. This, my dear friends, is a quadratic function, AR squared, so it should look like this. Okay, but notice I'm only taking radius greater than or equal to 0 because radius can't be less. Okay, so that makes sense why the inverse is the square root function, but I'm only taking the positive side of the square root. Okay, square root function. So here now, the radius depends on the area. So here is when, if you're given the area, you can find the radius by doing this. So this curve would have area here as being independent, radius as being dependent, and it would be a square root function, something like that. Okay, so these two functions are inverses of each other, but notice we did not interchange the variables because they have meaning. Okay. However, if you get something like this, where you just have x and y, we just want to interchange the variables. Now, we want to find the inverse of 2x squared minus 1, but we want to restrict this so that the inverse will be a function. So first, let's get a general idea of what this looks like. This is just a parabola that's been stretched by 2 and moved down 1. So it looks basically like this, right? With its vertex at 0, minus 1. Okay, now when we take the inverse of this, we're going to get this thing, right? It's going to look like this. So we don't want to take the whole thing because, why? Well, because that will make it not a function. So we only want to take one arm. We only want to take this arm. Okay, so that means basically that we only want to take the inverse of y equals 2x squared minus 1 for x values greater than or equal to 0. Okay, we always restrict on the x value of the vertex. Okay, because that tells us which arm to take. So now we just switch x and y. X equals 2y squared minus 1. And now we just rearrange so that we have y by itself. So we do x plus 1 equals 2y squared. X plus 1 divided by 2 equals y squared. And then go over here. Y equals the square root of x plus 1 over 2. Now, normally we would take plus or minus, okay, to do y equals. But because we only took this domain, we are only going to have x plus 1 over 2. So what will that look like? Well, instead of being at 0, minus 1, it'll be at minus 1, 0. Okay, and it will go in this direction. Okay, and there's our inverse function, which corresponds to this guy. Okay, so if it asks you for the domain and range, well, our domain here was x is greater than 0, and our range was y such that y was greater than or equal to minus 1. So the domain of our inverse function is just the range of our old function. So x is greater than or equal to minus 1. And our range is the same as this domain. So y is greater than or equal to 0. Because we restricted the domains, we have to use that one. Okay? Example 2. Volume equals 4/3 pi r cubed is the equation for the volume of the sphere. Determine the equation of the inverse by expressing r in terms of v. Okay, so notice here that the variables have meaning, so we can't interchange them. We just leave r where it is and move everything over until r is by itself. So v equals 4/3 pi r cubed. So first we divide both sides by 4/3, okay? Or you can do it separately. You can multiply by 3 and then divide by 4. So I'll do it that way just for those of you who algebraically have trouble seeing this. So this is being divided by 3, so we multiply both sides by 3. Now we divide both sides by 4. Okay, now it's pi r cubed. It's being multiplied by pi, so I get rid of that first. So I divide both sides by pi. Okay, now to undo a cube, we take the cube root. So you put the little 3 here in the corner, and that's equal to r. Okay, so you should write your final one as r equals, making sure the whole thing is going to be under the cubed root. Okay, don't skimp out on that. You got to make sure it looks like this whole thing is under the cubed root. And there you have it. Okay. Last example, find the inverse function of this. Okay, so this is a quadratic. Notice it has a vertex at 5, 4. Okay, so therefore we want to restrict the x value of the vertex. So we only want to take x's greater than or equal to 5. Okay, so we're going to interchange x and y. Okay, and now we have to think about what we can move over first. So first the 4. Okay, now divide both sides by 3. Okay, now we get rid of the square root. Okay, now because we're taking the restricted version, we don't need to take plus and minus, just the plus. Okay, and now move the 5 over. Okay, so now we can rewrite this with function notation. I guess I didn't need to write that quite so long, but there you go. And there you have it. Okay. So there you go. That is the note on inverse relations. Now, if you want to know what you can do to be successful, based on this note, you should be able to do all of the things here in the success criteria. So describe what an inverse is in your own words, be able to, write me something about it or talk to me verbally about it if I ask you to describe it. Discuss the relationship between the domain and the range of a function and then of its inverse, okay? And talk to me about why this is true. Why? If I give you just the graph of a function, you should be able to sketch its inverse using the facts that we talked about. And if you get in a question where it says find the inverse equation, knowing when it's appropriate to just switch the variables and when you have to keep them the same. Given an equation of a function, finding the equation of its inverse. And then also, if I give you a parabola, being able to find the necessary restriction so that its inverse is a function, okay? So just a little reminder here, if I give you an equation in standard form, you have to convert it into vertex form before you can actually do the inverting, okay? It has to be in vertex form before you invert. That's very important to understand, okay? Remember, to get it into vertex form, you just find the vertex using x equals minus b over 2a, okay, to find what the h value is and then the k value, and then the a values are the same. Thanks for watching. Hope you learned lots.